Afternoon, everybody. Welcome back to CENG 15. A couple of different topics for today. One of them is we're going to finish up a little discussion of iteration, a different way of doing an iterative loop, which is going to be called a while loop. We've done a for loop before. There's a very similar one called a while loop that you can use for different things depending on what you need it for. Are you going to sit down, buddy? Where are you at? Well, Mir was here. Mir has apparently decided that he doesn't want to be part of our lecture today, so he has wandered off. The other thing that we're going to do is introduce the idea of molecular dynamics simulations. So mostly just on a background case of like, when is this used? Who would use something like this? Why would they use it? What is it doing? Is always a good thing to understand. And then that will be the topic of our remaining simulation, which will take us through like the next 2 weeks or so. Just looking out towards the last few weeks of class, we really transition in the last few weeks of class to practical stuff in Matlab, right? It comes down to things like solve for x, right? What are all the different ways we can solve for x when there's one equation or three equations or nonlinear equations or linear equations or differential equations or stuff like that. So we wrap up the class with those really practical elements where it'll be facilitated by our understanding of how to interact with Matlab that we've been building up over the last few weeks. So our last simulation that we'll deal with is molecular dynamics. We've already done a random walk simulation. Within molecular dynamics, we'll probably tackle 2 different topics, and then you're going to do a couple of simulations both on your homework and the midterm. The plan for the midterm is not next week, but probably the following week. So I'll probably post it on either this coming Friday, not today, but like a week from now, or maybe the Monday right after that, and then you'll have until probably that following Friday. So you'll have either 5 or 6 days, something like that, to work on the midterm. But we'll talk about that in more detail next week when it gets a little bit closer and I kind of finalize the plans for the midterm. Before we talk about the while loops and the molecular dynamics simulations we're going to deal with coming up, I just want to review the information that I sent out in an email earlier, which is also now on our course syllabus. Oops, oh, we're on a window capture. We need desktop capture. There we go. Starting on Monday, i.e. 2 or 3 days from now, depending on how you want to count, in-person learning will be available again. So these lectures that I'm doing in here, which are currently in my garage with Mir, are going to be done in SME 302, which is the room that our lecture was supposed to be taking place in all quarter. Masks will be required if you want to show up. I picked, it was actually a fair amount of work to get 302. It's not a normal lecture room. It's one of the lecture rooms that's across the hall from the Maker Studio. So if you remember where that is from either your NANO 4 or your CENG 4 class, it's one of those lecture rooms over there. And we had to put in some work to get those rooms for us, reserved for this class. The great thing about that room is that there are laptops available for checkout. So if you want to come by during the lab hours or during the lecture times and you don't have your laptop, you can check out one of the laptops that are in there. You do have to complete the responsibility contract for Envision in order to check those out, but it's like a 7-minute video and a little quiz, which you can take as many times as you want. So if you want to use a laptop in 302, you can use your own, or you can check one out when you get there. Importantly, though, as I've mentioned here, the class is going to go on just like this, like we're doing right now, for the rest of the quarter. So there's no element of the class that will ever require you to be physically present. You can complete the whole thing remotely. About the only difference that you'll notice, if that's the route that you would prefer to take, is that if I'm being honest, the audio quality might go down a little bit. I'm going to try to keep it as best I can, but I'm going to be doing this inside of a lecture room. So it'll be a little bit different, right? It'll sound a little bit different. There might be some echoes and some bangs and stuff from the background. And I guess also, if you do show up and ask a question, your voice will probably get picked up by the mic. It's going to be one of these mics that'll probably pick you up. But just keep in mind, it's not required for you to show up. Based on the survey results, about half of you said that you were either very likely or somewhat likely to show up. So as long as those numbers stay up, right? If I start talking to myself, right, if it's an empty room that I'm talking to, maybe we'll revisit it. But as long as there's, 3 or 4 people a day or something like that, ideally even more, then we'll stick with it, and we'll keep it up until the end of the quarter. I prefer in person. I'm perfectly comfortable here as well, so I can do either one. Either one is good for me. So if you have any questions on that, please shoot me an email or throw it over in Canvas chat. Like I said, you can do the whole thing remotely. It's not going to change anything about when the class is offered. It'll still be here on Twitch at the regular times. Office hours will still be, available through Zoom. The only difference is I will also be in person. Right now, the plan is only for these in-person hours. So if it shows up on this schedule, I will be in SME 302 at those times. So you're welcome to stop by. I believe, I'm not sure, I might have to update this as I get more information. I think Breege is going to keep all of her office hours remote, so she's not going to have a physical office hours. So hers will look the same. I'll let you know if that changes going forward, though. So that's a big update about the class. Let's finish up our iterative stuff. So we're going to switch over to Matlab. One of the things that we're going to do going forward is a small change, but it does have certain impacts for what we're after. We're going to draw back on using Matlab live scripts, mostly because we need to be able to calculate things a little bit faster. One annoying thing about live scripts is they're a little bit more computationally intensive, right? You may have noticed when you open a live script, Matlab kind of chugs along for a moment there, right? As it's trying to open it and display everything that's on there. It's a little slower to run the scripts. Those are really nice for single homework problems where I want to throw drawings and math equations and all sorts of stuff like that onto a single document and have it all right there. But sort of the bread and butter in Matlab is just a plain script. Excuse me, not a live script. So we're going to start using plain scripts now. They're a little bit faster to run, but they don't have quite the same number of bells and whistles. They don't have like the sliders and the side-by-side display and stuff like that. So we'll see a couple of variations as we go. To create a plain script, though, rather than a live script, is pretty straightforward. It's about as easy as doing a regular live script. If you wanted a live script, you would say new live script. If you want a plain script, use the button right next to it. It's new script over here. You'll get the window to pop up here. One of the first things to note is that these scripts have only code. So scripts like what we're doing here only have code. There's no pictures, there's no plots, there's no sliders or anything like that. It's just code. We can still plot things. It's not like we've lost the ability to plot things. They'll just appear in a pop-up window as we're working through them. The other thing to note is that the extension of the file name is different. So these have extensions of .m, and sometimes that means they're called m files or m scripts or m something or other. And that's in comparison to what we saw with live scripts, which were .mlx. Plain scripts, the .m files, these are just text files. So you can open them in any text editor and they will appear just fine. Your text editor might complain like, this isn't a text file. Are you sure I should open it? And just say, yes, it's a plain text file. The .m just says, do it in Matlab. So although you can edit it in a plain text editor, I would not recommend it. I would recommend editing in here because Matlab is doing real-time syntax checking and highlighting, so it'll warn you if there's a problem. Warnings and errors show up on right. So if you do have a warning or an error or something like that, that Matlab can check for the syntax, you may notice it show up over here on this bar, which wasn't there. Actually, it was there in a live script. It was just a little bit less obvious. But there's also this green box that sits up here. Generally, we want that box to be green. We can get by if it's orange. If it's red, it means the script won't run at all. It's detected an error. That's just a syntax error. So we'll keep an eye on that, but I don't think we'll actually actively use it for anything like that. So let's go ahead and save this so I don't lose it. Lecture 11B. I think that's big enough. I don't think we need to zoom in too much more than that. I think you can see that okay at home. So that's a script. It's not a big change from a live script. It just means it's only code, right? So anytime I want to write like this, I'm going to have to do a comment or something like that. So let's talk then about for loops. This, by the way, is a comment. These are individual comments, and we can do a different kind of a comment like this, which is called a comment block. And it just looks like that. You put a percentage sign, and then you do an open curly brace, and then to finish the block, you use a closing curly brace followed by a percentage sign. It's just another way to do comments, so you don't have to put the percentage sign in front of everything. So I'm just going to use that here so that we can write some notes. So looking backwards, we just finished up a lot of work with for loops, and we are going to continue to use for loops a fair amount. Their iteration in general is going to be a pretty big feature for the next couple of weeks. So for loops are still there. Generally speaking, for loops are good if you know how many steps you need to take. In other words, how many iterations you need to make. So for loops are good if you know how many steps, i.e. iterations, to take. They are less good, I guess would be a word for it. I'm going to assume that that's proper grammar. They're less good if you don't know when to stop. Specifically, you don't know when to stop the iterations. There are a few common cases. That might seem like a weird thing. Like how can you design a simulation where you don't know when to stop? Like, isn't that something of a problem that I don't know how to stop something like that? There are a few common cases, though, where the simulation is set to run until a particular condition is met. The common cases when that happens, so when you don't know when to stop your iteration, there's two. One of them is if randomness is involved. And that's the one that we're going to practice here in a moment. But for example, let's say that we were doing our random walk simulation that we were working on for the last week or so. What if you wanted to say, run this iteration until the displacement from the origin exceeds, I don't know, 100 units, whatever the units are that you have on there? There's not really a great way to do that with a for loop. You can kind of set the number of iterations to be a lot, and then there is a way to tell Matlab to break a for loop. It's a little bit inelegant to do something like that. There is a tool designed to do something like that, which is a while loop. The most that we know from what we've studied about those random walk simulations is that on average, if we want to know the number of steps to reach a certain distance, there's that square root dependence between the number of steps. If you square that, that is proportional to the distance that you've traveled from the origin. But it's not exact, right? That was just an average over a lot of simulations. If you wanted to stop a simulation exactly when it hit that condition, a for loop's not really what you want. A while loop is what you want. The other way that you can do, or the other reason you might want a while loop, is if the simulation itself is complicated. And what I mean by complicated is not necessarily that the code is complicated. It's that the behavior of whatever you are simulating is more complicated than you want to do the math for. So for example, we're going to look at ideal gases in fairly short order. And if we want to stop, let's say we simulate the ideal gas going across, hitting a wall, maybe colliding with another particle or something like that, and you want to say, I want to run this until I get 50 collisions or something like that. Because the initial conditions of exactly how fast all of those molecules are going and which way that they're headed and whether they hit a wall or a particle or what, because those, even though those rules may be straightforward, the multiplicity of their interactions makes it such that it's really hard to predict ahead of time exactly how many steps I have to take in my simulation in order to get 50 collisions. It's easier to say, let's just make a little counter over here, and every time something collides, tick that up by 1. And when you hit 50, stop running. That's a more straightforward implementation in code than sitting down, say, with pen and paper and trying to calculate the trajectories of everything. if you could do that with pen and paper, then you wouldn't be doing the simulation anyway. So they kind of fit nicely together with something like that. In these two cases, as I said before, we use a while loop. We can use a while loop. A while loop will have a condition that's set up on it that says, keep doing this iteration infinitely until a particular condition is met. While loops can become infinite loops if you're not careful about the way that they break their condition. It's not going to blow your computer up or anything like that. It'll just temporarily lock up Matlab, but it's easy to give Matlab a break on your keyboard and say stop your infinite loop. So we're not really worried about infinite loops. So as an example, the example that we're going to do today, let's generate random numbers, specifically random integers, and we'll generate them from 1 to 20. Actually, let's do 1 to 15. 1 to 15 will be a nice small one. And we're going to continue generating until one of the numbers is greater than 13. Stop when a randomly generated number is greater than 13, i.e. whenever it is 14 or 15. So it should happen some of the time, right? If we're generating with equal probability an integer between 1 and 15, a little bit somewhere around like what, 90% of the time it'll be okay, 80% of the time it'll be okay, 85. But every once in a while we'll generate a 14 or a 15, and that is supposed to be our key to stopping our simulation. The general syntax of a while loop is that you say while, of course. So for example, while, I think I messed up my, that's supposed to be that way. We need to name it something like that. So let's just say that it's my number. The condition that you set here is when do I want to stop? So, or more specifically, when do you want the loop to continue? So I would like to continue as long as my number, which presumably we are going to randomly generate, is less than 13. Actually, let's say if it's less than or equal to 13. If it's less than or equal to 13, that means if it is 14 or if it is 15, the loop should stop. If we said it was less than 13, it would have also stopped on 13, which it could very well generate. So that's the basic syntax. You put a while condition here where we have my number is less than 13 is the condition, right? That is the condition for the while loop. You don't actually always have to supply a condition, but every time that we're going to write a while loop, we're going to have a condition that's associated with it. We don't want to run, actually a lot of things run infinite while loops. Virtually every program that you run is running an infinite while loop because it's checking for updates, like video games run while loops nonstop. So we're inside of the while loop. What do we want to do in there? Well, this particular problem, we just want to generate random integers. So what we want to say is my number is equal to a random integer between 1 and 15. What do we want to do with that number? Not very much. Right now we're just going to display it so that we can see what's happening inside of our script. If I try to run this script, I'm going to get an error. So let's run it. And see what the error is and see what it means and how it relates to other stuff. So I get an error, and it says I have an unrecognized function, my number. Errors in Matlab are, sometimes they can be very obscure, but other times on the types of scripts that we're working with here, there's at least some hints there that can help you. Sometimes these hints are buried like so deep down inside of like built-in Matlab functions that it's like, I have no idea what you mean, and you just got to stare at the code until you figure it out. But sometimes the error message is really helpful. First of all, it's telling us where the error is. That's the script, right? The error is happening in lecture 11b.m. The next thing it tells us is the error is happening on line 22. So I can come up here and I can look at line 22. And then it's saying, well, the problem is that I don't know that there's a variable called my number, right? So it's saying here when you tried to evaluate this, I didn't know what you meant. And so that's our first clue as to how a while loop works, is remember code works from right to left and top to bottom. So the computer started reading down this way, it hit line 22, and the first thing that it did is try to evaluate this statement. It tried to say, what's my number? Is it less than or equal to 13? In fact, the very first thing it probably did was figure out the number 13, and then it compared my number to that. The problem is over here in the workspace, there's nothing here. Right? There's no my number, and so it didn't know how to compare it. It doesn't exist. So like a for loop, we have to do something that creates those variables ahead of time. In a for loop, we called that pre-allocation. So we had put in a bunch of zeros so that we could stuff numbers inside of them. In a while loop, we don't have to pre-allocate. In fact, as we'll see in a moment, pre-allocation is kind of hard because we don't know how many steps we're going to take. Why are you staring at me? He's such a creeper sometimes. Like he'll just walk up to me and he's got these big old brown eyes and he just stares up at me. Sit down, buddy. It's fine. We're going to be here for a little bit. Oh, okay. All right. He's going to sit down, he says. So instead of pre-allocating, since we don't know the length that we want, and yet on the other hand, these things have to exist, sometimes we say that variables have to be initialized. In other words, they have to exist. Right? If a variable doesn't exist when it is used in a condition for a while loop, you're going to get an error because the very first thing the while loop does is check that condition. That also implies a somewhat unusual behavior of a while loop that didn't really make sense in the context of a for loop, which is that it may be possible that the while loop never executes at all. If the initial condition is set, or if the variable involved in the condition is initialized so that this initial condition is false, the while loop will simply not run. That may happen. There may be times where that's useful. For the most part, for us, we would not do something like that. But we need to initialize that number to be something so that the while loop iterates at least once. So let's initialize my number to be something that will ensure that this loop happens at least once. So we'll set my number initially to be 0. Actually, let's pick something else. Let's make it 3. 0, for some reason, feels like a special number in coding, probably because it's all zeros and ones. Let's show that it can really be anything. We'll just set it to be 3. So here we are initializing a variable. And specifically, that variable is used in the condition for the while loop. So now if I run my script, and we look down here at the command window, the results are being printed down here at the command window, and the variable is showing up in our workspace. So let's run this a couple of times and see if we can detect a pattern, because we can. So I just ran that first, and I got a 13. That's good, right? It kept going. Then it generated a 14, and it stopped. The value that I got out was only the number 14, right? If I look at the variable editor, the only thing that I got out is the number 14. I did not get out 13 and 14, but I displayed 13 and 14 because I asked Matlab up here with this DISP function to display a number. So this function is to display a number. You could get away with the same thing by leaving off the semicolon, but that turns your square orange, and I just don't like an orange square. It would do the same thing if you just left off the semicolon. So let's run it again. I'm hitting F5. The way to run a script is about the same as the way to run a live script. So up in your ribbon, there should be a big green run button. I'm hitting F5 on my keyboard because I'm accustomed to doing that. So I ran it again. I got a 2 that time. I got a 14. My number is 14 because that's the last one. Let's run it again. Okay, this time I got a slightly longer string of numbers. I got a 10, a 2, a 5, a 9, and a 15. Notice my number is only 15 over here. Often what we want to do with something like this is actually watch or actually collect these numbers. The way that this script is running right now, we're not accumulating these numbers anywhere. We're not storing them anywhere. We're just generating them and then overwriting them. We can watch that too with the debugger. So I know we had mentioned the debugger at the end of last lecture. A while loop is a good place to watch a debugger work too. You can run the debugger in a script the same way that you can a live script, you just click on the little bar that's next to the number instead of the number itself. And that'll cause this little circle to show up. And now if I run this script, I am now inside of the debugger. Let's restore the tool strip up here so we can watch it. The green line is telling us where we are. Right, so this little green arrow is saying that's where you currently are. And then we're going to watch the workspace over here. And I think because of the way that my little thing is set up here, yeah, it keeps moving the display. At any rate, you've got those same buttons up here, right? You've got a continue button, a step button, in, out, run to cursor, and quit debugging. So if we just click step, we can actually watch MATLAB work its way through each one of these. If I click step here, we'll see that my number is supposed to be set to 3, which it is. And then we'll step inside of the while loop. So it'll generate a random number. We see my number change to 15. It will display it. So we got the number 15 out here. And then it will loop back up to the top and make that check again. That happens to be a 15, so the check failed, right? It said, nope, that's greater than 13, so that's it, we're done. And that's the end of the script, right? If you keep clicking run, it'll just finish the script. If we do it again, we can eventually get to the point where we can watch it step through. Here, my number was randomly generated to be 3, so it'll display a 3 and loop back around. Now we got a 15, so it stopped again. It's not a very exciting one. Let's see if we can get a few more. Nope, that was a 15. Hey, there we got an 8. Okay, 8's not bad. There's a 13. It's not bad. And a 3, and a 7, etc., etc. Finally, it got to a 14, and it made its way back around. So the debugger, if you use the step function, will step through each one of these, and you can watch the numbers get randomly generated. And that's very helpful for understanding what your for loop is doing. It's not always easy to understand what it's doing. But what if we wanted to collect these, which oftentimes we do? What if we wanted to collect this list of numbers here? For example, this one was 15, 18, 13, 3, 7, and 14. What if we wanted those in a vector? We have to bend the rules a little bit for how we do something like that. Because previously I said one of the rules of indexing is that the thing has to exist with the right number of components, right? We can't index into anything beyond the last element or before the first element. It's still true that we can't go before the first element. There's no way to index prior to that. But we are now going to look at a way that we can bend that rule. There is actually a way that we can go beyond the last element and put another element there. In fact, there are a couple of different ways that we can do something like that. The first thing that we have to do, though, is like the initialization of my number, and similar to the way that we pre-allocate with a for loop, we do have to initialize whatever variable we want to hold all of those numbers. So I'm going to call that my vector of numbers. And what do I want the first thing to be? Well, it kind of depends on what you're trying to accumulate. In this particular example, I want the first value to be my number, right? That's option 1. Option 1, put the first value. But sometimes there is no first value. Sometimes the first value won't be generated until you're somewhere inside of your simulation. So maybe it's not an actual number yet. You just know you're going to need the thing sooner or later. So there's another way to do that in MATLAB. You could also say my vector of numbers is equal to an empty vector. This is option 2, is to create an empty vector. It's two different ways of doing a similar thing, right? They're both initializing this variable that we want to call my vector of numbers. It's just initializing it in different ways. This one says, I already have an idea of where that's supposed to start. The first value is supposed to be my number, right? In this case, it's 3. The other one is saying, I don't really care what's been generated so far. I'm starting from a blank slate. There's nothing in that vector right now. Let's just leave it empty. We'll leave it this way with my number so that we always see a 3 initially, right? There's always going to be a 3 that sits inside of there. How do we take the next my number, right? This one. Once we generate that, how do we glue it on to the end of the existing vector of numbers? There's about 2 different ways to do it. One of the ways is to use that special keyword end that I showed you before. So my vector of numbers can be, if we wanted to index into that, right, we want to take my number and put it inside of there. So there's going to be some kind of an index that goes here, and we're going to put my number in there. This is using indexing. What goes inside of here? Well, the end keyword gets us close. Normally that would mean just go find the end of this list of numbers and put this number here, put my number here. But the rule bending that we're going to do is to actually go one step beyond that. Say, this is the end of the vector, go to the next one. Create a new value right there and put my number in it. Create a new element and put it there. Matlab will complain when we do this. So you'll notice my vector of numbers is now highlighted, or it's underlined in that orange squiggly. There's an orange bar over here, and there's an orange square up here. And so if you kind of backtrack what that is and eventually just hover here, you'll see the error message that we're getting. It's not actually an error, it's a warning. It says, this variable appears to be changing size every loop of your iteration. You might want to consider pre-allocating this for speed. That is in line with what we had already learned, where I said pre-allocating stuff is usually the best way to go because it's faster for Matlab to have an existing list of numbers and then just take a number and put it in at a various location. This is an example, though, where we're just going to have to grit our teeth and bear it. There's nothing that we can do. We don't know how many elements we need, so we're just going to stick it at the end, and that vector is going to grow and grow and grow. As long as you're not getting out of control with this, like if you're only doing it a few hundred times, it's not going to slow your code down very much. As we get to more and more simulations with like 5,000 and 10,000 steps and stuff like that, that could become more of a problem. It could be noticeable that we're not just indexing into an existing pre-allocated vector, that we're actually appending to the end. That's not probably going to be a problem anytime soon. So this is append to the end using indexing. So if I now run this script, the display is still working over here. I've got 12 and 15. And if I look over here at my vector of numbers, I see that it's a 3, a 12, and a 15. So it's not quite the same as what was being displayed, because remember, display is not operating on that first one, right? There was the very first thing that happens inside of the while loop is a brand new random number gets generated. So the 3 never gets displayed, but it was captured inside our vector of numbers because I started it out with a 3. Here you can see we've got a 3, a 12, and a 15. If I run it again and look over here at my vector, I can see I've got this time a 3, a 10, a 1, a 13, and a 15, which more or less matches what's being displayed down here at the command window. Again, it's just off by 1 because of that display. To mute that display, because I'm kind of tired of looking at it, I'm just going to put a percentage sign in front of it because we don't really need to watch it display anymore. So this is one way. It's append to the end of the vector by using indexing. There is another way to do it that I want to introduce because it's a style of coding that looks funky if you're used to algebra, but is very common in programming languages. The other way to do it is to either update or overwrite that variable by using it on both sides of the equal sign. So we can do something like my vector of numbers is equal to, remember the way that we first learned to assemble vectors was to use the 2 square brackets and then just put the numbers inside there separated by a space. We can do that same thing even if one of those numbers is already a vector. So we can say something like, take the existing my vector of numbers, that's the first element in our vector, and then put another number after it. And which number do we want after it? We want my number to come after it. So we put a comma here. This is an example of appending by what we would call concatenation. Concatenation. Or appending by concatenating the variables. It's not unlike the ampersand that we saw in Excel. This is a different way of doing essentially the same thing that was here. It does have one advantage that I can think of off the top of my head. It doesn't have like that many advantages. It's doing the same thing. But one advantage is that if I run it like this, I will get exactly the same kind of thing that I was getting before, which is a row vector of values, right? It runs off to the side. This is nice because I can switch back and forth between row vectors and column vectors just based on the way that I'm appending things here. So this specifically will give me a row vector by appending. If I take exactly that same thing, let's copy it up here. Let's remove this one because I don't want to know this one. Why did it do that? Oh yeah, that's what I want. And all we have to do is change that comma, right? If we replace that comma with a semicolon, now we don't get a row vector, we'll get a column vector. Because remember, the semicolon says, build this up, but take the next one and put it underneath. And then there'll be 2 elements. And then it'll say, start with the 2 elements and put the next one underneath there, and it'll be 3 elements. I kind of like column vectors more than row vectors, simply because it's easier for me to see them over here in the variables window. Right now I get this nice list of 3, 6, 9, 14, 12, 4, 8, 11, 14. It's very easy to see them. It's not fundamentally any different, right? It's just one's going in a 9 by 1 orientation. If I had left this the other way with the comma, it would have been 1 by 9. That's the only difference between them, is just what shape it is. But it's a little bit easier, I think, for me to read doing it as a column vector. So I tend to do it that way if I need it. My own preference when I'm coding things, if I can't do it, or if I don't need to do it this way, I will personally use the indexing version, only because I'm comfortable with it. But they're both achieving the same thing. So whichever one feels sort of more intuitive to you, it's okay. Let's take a moment and really understand the order that this is working in, because it's going to be important here in a moment. Did I drop my pen? Oh no, there it is. This can feel a little bit weird when you initially see it, because you appear to have a variable over here. Let me give myself some space here, just so that we can write a little bit. There we go. So we appear to have a variable over here, right? Let's call that just x, so it's a little bit easier to write. And then I have another variable over here. So it looks like I'm doing something along the lines of x is equal to, say, x and then a number, right? Conceptually, this is what I'm doing. That looks a little bit funky if you've been thinking of the equals sign as the algebraic style equals. Because if we were doing algebra and we did something like x is equal to x plus 1, and I look at that and I think of that like an algebraic expression, I might rearrange that, or I might be tempted to rearrange that to say x minus x is equal to 1, which would result in a contradiction of 0 is equal to 1. This is not how code works, though. Remember, code works, it first evaluates the right, it assigns it to the left, and then it goes down to the next line. So when you see something like this, what it's doing is it's first evaluating the x. It just becomes a number as far as Matlab is concerned. Then it evaluates the number over here. It bundles those into a number through concatenation. And the equal sign is not an equality, it is an assignment operator. So it's taking the result of the stuff on the right and it is assigning it to whatever variable we have put on the left. So you really can in code write something like x is equal to x plus 1. And what this means is increment x by 1. Increment x by 1. This sort of general process, there's a couple of different ways that I am in the habit of calling it. It might be updating. You might say, for example, I want to update the value of my vector of numbers. It could be increment too. Oftentimes, this is called incrementing. So it's either increment or incrementing. That usually refers to this kind of an operation. Whenever you take a variable and you say, there's not much I want to change about this, I just want to add a number to it. That's incrementing. And I bring it up here just because it naturally appears when we're talking about while loops, because one of the primary ways that we generate numbers in while loops is through a process that looks like incrementing. So suppose we wanted to know how many iterations we've done. We could say number of iterations is equal to, say, 0, right? Maybe we haven't started any in here. And then we can write a fairly unusual looking statement inside of our while loop that looks like number of iterations is equal to the same number of iterations that I had before, plus 1, right? This means increment by 1, right? Take a 0 and add 1 to it. The next time the loop comes around, take the 1 and add another 1 to it, and you'll get 2. And so if we run something like this and look not at the my vector of variables, but the actual workspace, we can see the number of iterations is related to the length of the vector. We started it off at 0, so let's set it at 1 just so it looks a little bit better. Number of iterations is now 10. If I run it, let's get a shorter one in here. Actually, 11 works too. Based on the size of my vector of numbers, we must have iterated 11 times, right? Because there are 11 numbers inside of there. Technically 10, because we started at 1. The number of iterations value that we have here looks like it counted up in the same way. And that's often helpful. This is an example of a counter. And it doesn't have to be a fancy name like number of iterations. It could be something like 0, and then we could make another counter that looks like x is equal to x plus, I don't know, 3, right? And now x will count up by 3 each time we go through. So you can see here x got a lot bigger, right? It was 57 instead of 20 or something like that. Or we can set it to be essentially the same by making it 1. It's not necessary to increment by 1 or starts at zeros or something like that. What I'm trying to get to with a statement like this is this idea of you can make a counter inside of a while loop. You can also do indexing this way, right? You can say maybe my first index is 1 or 0 or whatever. Maybe we'll make this one 0. You can also increment an indexing value like this to say index is equal to index plus 1. These are all variations of counters. I'm just going to change the numbers here so that you don't think there's anything special about the way that we are indexing them. They can start off at absolutely anything that we want. Maybe I'll just put some numbers in here. It doesn't matter exactly what they're starting with. I don't want you to think that a counter has to start at 1 or 0 and can only increment by 1 or 0. It's just different ways of that process of incrementing, of taking the old value and adding a new value to it. It's not unlike what we've seen with the random walk, where we had an old value and we added a change to it and got a new value. It's just that this happens to be all in one variable. It's not that those numbers are going different places, and that's perfectly okay inside of really any programming language. They should be okay in any of them. So that is while loops. For anybody who's watching carefully or who reads this stuff, you're going to need this on the midterm. So make a mental note. You're going to need a while loop on the midterm. But that's sort of the end of the introduction of a while loop. All of the code that happens inside of there, other than counters and appending things, works the same as the code that we've seen in a for loop. So you can still do all the other stuff that you can do inside of a for loop. So I'm going to wait here for about 2 minutes, and in the last 5 or 6 minutes of class, we're going to introduce that new idea of molecular dynamics. So I'm going to shut up for a moment, give you a moment to catch up with what I've got here. Remember, I'm always over in Canvas chat, so if you've got any questions while we're sitting here, throw them over there. But I'll come back in just a second, and we will wrap up our Friday class with molecular dynamics. Okay, no questions so far, so we're just going to have a little discussion here at the end, so no more notes or anything like that. Let's switch over to the web. Oh yeah, we don't need this, we need Firefox. So there was an article that came out in the Times a little while ago, New York Times, about the coronavirus. One of the things that we can do with computers is take lots of very simple steps a lot. And by a lot, I mean a lot. So what you're looking at here is the result of a molecular dynamics simulation, which did exactly what the text says it does. It put the coronavirus in a tiny droplet. So that purple thing that shows up every once in a while, that is a coronavirus. Everything around there are elements that you see from aerosols that come out of your mouth or out of your nose. So there's lung surfactants in there. There's proteins that are inside of your lungs. There's obviously a lot of water. There's ions. And then there is, of course, the coronavirus. This came out in December. I pointed out partly because it's unprecedented, the size of something that we've been able to do with these simulations. There's a lot of particles inside there. So if you look here at the caption, there's 1.3 billion virtual atoms in there. That is like mind-boggling, because that means every 1.3 billion of those atoms is represented by at least 3 numbers. So you've got something like 3.9 billion numbers just to represent the positions of the atoms, because they're in 3-dimensional space. That is like nuts. The other really neat thing about this is who did it. The person who did it is Professor Amaro, I'm not sure how to pronounce her name, but she's here at UCSD. She led the effort to do this. It was absolutely multidisciplinary, and I want to take a few minutes to let her explain what she did, because we're going to be starting with like the basics of how these molecular dynamics work. We don't have supercomputers like her team does, so we're not going to simulate this. But we're going to do some of the same ideas. So I'm going to switch over and watch a couple of minutes of her video to get us started.
Take a deep breath in and breathe out. You may not think about this very often, but every time you breathe, you are producing thousands of tiny microscopic aerosol particles into the air around you. When you breathe in, you're inhaling your own aerosol particles as well as those made by the person sitting next to you or exhaled by anyone else with whom you're sharing the room. If someone in the room is infected with COVID-19, their aerosol particles will contain the SARS-CoV-2 virus. Over time, those virus-laden aerosols will build up, especially in poorly ventilated spaces, increasing your chance for infection. Scientists have been able to simulate the transport of these particles, showing how large droplets settle quickly and how smaller particles stay suspended in air for hours and travel long distances. These smaller particles, called aerosols, are particularly challenging to study, in part because they are so tiny, but also because they are highly dynamic, and because we simply have not yet developed tools to let us see inside aerosols at the atomic level. That is, until now. Here, we are using all-atom molecular dynamics simulations as a computational microscope to give us never-before-seen views inside a virus-laden respiratory aerosol. This method allows us to build up the aerosol atom by atom, accounting for all of its chemical and biological complexity. We then model each of those atoms as hard spheres, define a potential function that describes the interaction of all the atoms in the system, and then we integrate Newton's equation of motion over time on the most advanced HPC architectures in the world to build up a dynamical understanding of the aerosol and its molecular components.
All right, so she said a couple of things there that are going to be relevant to us. The first is that we often will model atoms as hard spheres. Depending on the shape of the molecule, we can also model the molecule as a hard sphere, but the more sort of oblong or not abstract, non-spherical the molecule gets, the worse that approximation ends up being, But an atom is to a very good approximation a sphere, especially when we're dealing with molecular dynamics simulations that are interested in behavior of atoms on a continuum scale, on a large scale. If you're interested in quantum mechanics, there are quantum mechanical simulations. For example, the most common one is called a density functional theory. Well, a simulation that uses density functional theory. And we do have folks here at UCSD that do those sorts of things at the quantum level. And those are usually restricted to a few molecules, and usually fairly small molecules, but they can get fairly big. A molecular dynamics simulation is usually better suited to modeling the interaction between lots of molecules. For example, billions of molecules that we have on here. And we do that by modeling them as hard spheres. The other thing that we do is what she mentioned at the end, which is we integrate Newton's equations of motion, which is what you see here. Don't underestimate Newton's laws. Like, they are fantastic. They apply almost all the way down to the atomic level. Like, if you were to look at the atom itself, yes, everything the electron is doing is quantum mechanical. But as soon as you look just slightly outside of there, right, if all you're interested in is the behavior of the outermost electrons and how those impact the other molecules around it, we've got a pretty good handle on that just through Newton's laws. The challenge that her team met, and that we're probably not going to do, is, of course, A, scale. We're not going to do billions of molecules. But B, this force parameter that we've got here, the actual force in between the atoms, is based on what we call an interaction potential. The interaction potential can be modeled very accurately. So there are lots of different terms in here. We can account for bonds. We can account for angles between atoms. I don't know what the dihedral is down here. It's probably another angle thing. This is talking about the interaction forces just between uncharged molecules, and this one is talking about the interaction forces between charged molecules. The ideal gas, the beauty of the ideal gas, is that all of that is equal to zero. So it simplifies our computations a lot because Newton's laws simplify to essentially ballistic motion. Things travel in straight paths until they hit something. They have to physically collide with something. A collision is often modeled through this term right here, but we're going to look at a different way to model collisions inside of molecular dynamics simulation. So this is where we are headed. We're probably going to spend all of next week setting up our simulation, and that'll give you enough background. We'll be able to set it up pretty fast just on Monday so that you can do the homeworks, and then we'll explore different ways of looking at those MD simulations. So I'm looking forward to getting back in person on Monday. Remember, you are perfectly capable of completing a class remotely. You do not have to show up in person, but I'm looking forward to being back in person on Monday. Our lectures will still be over here on Twitch, so if I see you here, I will see you here. If I see you in person, I will see you in person. Either way, have a great weekend. Stay safe, stay healthy out there, and we will see you back here on Monday. Have a good one, everybody.